So welcome. Today we'll be discussing Shor's algorithm. In particular, we will focus on the quantum part of it, which is essentially an order-finding subroutine that uses a quantum phase estimation algorithm. Now, Shor's algorithm tries to factor a n-bit number, capital C. Now, like many quantum algorithms, actually, Shor's algorithm heavily rely on classical computation first. So the first part of Shor's algorithm is try out classical methods to factorize number C. In particular, there are simple cases where one can easily extract the factor of C. The simplest one is when C is even, and then we output 2 and we stop the algorithm. Another case that can be efficiently computed classically is that C is equal to an integer number to the power another integer number. In this case, we can efficiently, in a classical way, compute A and output A and stop the algorithm. If none of this work, then we go quantum. And in particular, what we do is that we first choose a random positive number x that is lower than C. We then classically find S, the great common divisor of x and C, that we call S. Now, if S is different from 1, it means that x factorizes C, and then we have been very lucky, and then we can just output S and stop. If S is equal to 1, then we need to find quantumly the order R of x modulo C. If R is an odd number, we fail. As we saw before, the relation between order and factorization only applies when R is even. So if we find the odd order R, then we need to repeat the algorithm. But if we find an even order of R, then we can extract the factor of C, as we discussed in the last lecture. Now let's see how order finding and quantum phase estimation are related. To do so, we introduce the unitary U that acts on a state Y in the following way. Essentially, it takes the unitary U, it multiplies Y by X, and takes the modulo of C. Now, this is something that we can use the quantum estimate to get insights on. And in particular, I remind you that the quantum phase estimation algorithm is something that looks like this. So essentially, we first add a MARD, m qubit in the state 0. Then we apply a sequence of n qubit control unitary on a state, on ideally the eigenstate of the unitary U. And then we extract the phase by just inverse Fourier transforming the m qubit registry and measuring the results. Now, that was just the shorthand notation of the quantum phase estimation algorithm, but in reality, it actually is a bit more complicated because we have m qubits and n qubits in the two different registries. And in particular, we need to apply this unitary matrix several times in order to make this quantum phase estimation work. In a naive approach, actually, we need to apply this operation an exponential number of times as the size of the qubit, as the size n of the number increases. However, what we can do is do some trick to reduce significantly the number of operations that we need to apply. This is just seen by using this very simple relation. Essentially, instead of applying the unitary 2 to the j time, we can pre-compute x to the power 2j modulo C by using modular exponentiation. Once we pre-compute these values, and we just need to pre-compute it once, we can implement directly the operation of x to the power 2j modulo C times y. So let's see the complexity of this simple algorithm. The modular exponentiation requires n to the power 2 times m operation, where n to the power 2 is because the multiplication scales as n squared, and m is the number of times we need to apply the unitaries now that you did the modular exponentiation trick. On the other hand, we then also need to multiply every time the modular exponent times the code word y, and this gives another n squared to the m times m operations. And if m, the number of the bits in the two registry is equal, which is enough to estimate to a reasonable order the order of the number, then we can get a polynomial complexity that scales as O to the power n3. Let us now make a short recap of how the quantum phase estimation algorithm works, and especially apply to the case that we are examining now. So the first step is the Hadamard transform of the m qubits that will be used to estimate the phase. And when we do the Hadamard transform, we create the superposition of all the possible states in this m qubit registry. Then what we need to do is to apply the unitary operation several times with different control qubits in the upper registry. Now, as we discussed before, this can be done efficiently in O to the power n square times m operation, and this is using modular exponentiation. Now let's see what happens explicitly when we do this. Essentially, we apply the unitary and a number of times that depends on which qubit is the control one, and at the end of the day we get a state that looks like the following state. Now, more explicitly, taking into account the actual action of the unitary that we use here, that what we have is a state that looks like this. Now, this seems a very complex state, but one can recognize that the registry in this state can be very nicely rewritten into x to the power z, where z is a binary number. So at the end of this circuit, what we are left is just a simple state. There's a superposition of all the state in the qubit registry. We've multiplied by the y state, which is an eigenstate of the u unitaries modulo c. Now, the quantum phase estimation then returns the estimation of the phase of u of y. In particular, it returns in the upper qubit registry the phase phi, up to a precision of m bit. So we have assumed so far that we can prepare an eigenstate of the unitary u. So let's see how this eigenstate looks like. The eigenstate of u can be decomposed into this form, where r is the order of x modulo c. Now, this is very interesting because it shows that there is a relation between the quantum phase estimation and the phase that we extract and the order of the number. In particular, the phase that we extract will be dependent on some number s, which is the labeling the eigenstate, over the order r. However, we also can identify a problem, because the eigenstate that we need to prepare will depend on the order, and the order is what we need to find. So there is an intrinsic problem here, because we cannot prepare something that we need to find. To get rid of this problem, there are clever tricks that one can play. In particular, we can make a combination of eigenstate that is independent of R. To do so, we can take essentially an equally probability, the sum of all the possible eigenstate of U of R with an equal probability. Now this actually simplifies quite a lot and it reduces, just by looking at this, just by identifying this sum as a Kronecker product, we can easily see that this equation reduces just to a very simple state, which is x to the power k equal to 0 modulo c. Or in other words, this is the decimal number 1. Once again, this is not the state 1 where all the qubits are in the state 1, but this is actually the decimal representation of the number 1. So now we can, now that we have an input state that is a combination of all the eigenstates of the unitary that we want to use, which is x to the power j modulo c, then we are actually ready to go. In particular, we can apply the quantum phase estimation with these input states, and once again this is a binary, this is the decimal number 1, and we can apply the quantum phase estimation algorithm to, at the end of the day, extract an estimate of the phase S of R for some unknown integer S. Now, the main problem here is that what we have at the end is just some ratio of some unknown number and the order R that we want to find. So we still need to do a little bit of classical post-processing to extract R from this equation, from this number that we find. Luckily, this can be done very efficiently by an algorithm that is called continued fraction algorithm, that enables us to extract R from the ratio S over R with unknown S. So let's see now what is the success probability of the quantum phase estimation. Now, there are several reasons why this algorithm could fail. In particular, if we extract an odd value of the order R, then we need to repeat the procedure. If R is such that x to the power R over 2 is equal to -1 modulo c, actually also we need to repeat the procedure and we need to call it a failure. And also there is some finite probability that also the post-processing, the classical post-processing, for example, the continued fraction algorithm would fail. But all in all, the success probability is order 1. What this means is that it doesn't depend on the number n of the bit. And it's not, most importantly, it's not growing as the qubit, as the number to factorize increases. What this means is that, in terms of complexity, the classical subroutines are efficiently done. So the first part of the Shor's algorithm can be done polynomially in the size of the number to factorize. And the quantum subroutine is also polynomial. And as we discussed, it scales with n to the power 3, with a success probability of order 1. This has to be compared with the best classical algorithm that roughly, up to logarithmic correction, scales as an exponential of n to the power 1/3. And therefore, Shor's algorithm provides an exponential speed up.